We switch gears a little bit, and now we'll talk not about health optimization, but about AI. And the next speaker is Dima Kalupin. He's a founder of Unlock Biology, a startup that is focused on modeling cells in silico. Dima is a founder of several other companies. He and a community of science popularization. And also Dima loves both cats and dogs. That's what he said to me how to introduce him. So please welcome Dima Kalupin. Do we have technical problems?
Yeah, that's fine. Hey, thanks. Yeah, I think that hopefully my talk would be inspiring, but of course there are lots of problems, so I'll focus a lot on the problems that we have in modeling the cells. Yeah, a few words about myself. I have a background in pure mathematics, and I worked a lot in engineering, did some machine learning for high-frequency trading, and then did some business studies, consulting, startups, and communities. And for the last year, I've been focused on trying to make my contribution and found really cool people on the frontier of data generation for biology. And we believe that we have very nice ideas about how to eventually be able to have the foundation models for biology. But of course, it will take a lot of time. So yeah, this will take a lot of time. A question to all of you. So how much progress, from your perspective, have we made to defeat death? Who thinks that we made more than 50% of the progress already as humans? More than 25%? More than 10? Nice, so optimistic people. More than 1%? Okay. More than I'm actually here. So yeah, I think that we still need to make a lot of progress, but we can compress this progress in terms of time because we are now able to generate much more data, we understand much more stuff, and with AI coming, everybody will be able to have a scientific institute themselves and have a bunch of really cool AI agents, professors running the experiments, but this will take a lot of time. And most problematic thing is data generation. So I have to show you one very pessimistic video.
Rice, but the number 52 factorial is larger than the amount of love big numbers, but this and this are pretty hard to visualize. Numbers like 100 and 10,000 are easy to visualize as rice, but the number 52 factorial is larger than the amount of atoms in this pile of rice. In fact, it's larger than the amount of atoms in the entire world. But this gives us no sense of scale. I can't fathom the size of the planet, and I can't see how many atoms are in this bag of rice. So a better way of visualizing this is time. Imagine you set a timer for 52 factorial seconds, standing on the western coast of Ecuador on the equator. Wait 1 billion years, then take one step forward. Wait another billion years before your next step, and so on. When you've walked all the way around the world, take a drop of water from the Pacific Ocean and set it aside. Continue walking around the world, taking a drop of water every time you lap the world. Once you've emptied the Pacific Ocean, place a single sheet of paper on the ground, refill the Pacific Ocean, and repeat the previous steps. Once your stack of paper reaches the sun, your timer won't even be 1% complete. This is the amount of ways that you can shuffle a standard deck of cards.
Yeah, so that's the problem of computational complexity. So probably no one in humanity has ever shuffled the deck of cards in the same way as someone else. So statistically, it's practically impossible. And the processes in the cells are obviously much more complicated than the processes in shuffling the deck of cards. And can we now?
Not big numbers, but this and this are pretty hard to visualize. Sorry. Numbers like 100 and 10.
Yeah, thanks. So yeah, so that's a problem. Even when we have enough data, even when we understand the processes completely, we would not be able to model them directly. If we take Schrödinger's equation and try to take into account all the positions of the atoms and their interactions and so on, it would not be possible, even if we fill the solar system with quantum computers working perfectly and they work all the time with the universe, probably they will not be able to simulate the cell directly. And we still have a lot of optimism in terms of modeling this indirectly, and I'll try to, like what our company is doing, we model how the cell states change over time and when you do something to these cells using machine learning networks. But first of all, we need to see why it's important. And next week there will be more radical approaches presented around cryonics and replacement. And the ultimate goal in generation of data in biology is to have advanced bioengineering. So we want to be able, this is from the presentation from Longevity Biotech Fellowship, which I recommend to everyone who is interested to get into the field. And there are basically two big problems. One of them is related to collecting the data and being able to model what is happening. And another of them is related to delivery of the eventual changes that we want to deliver to the cells. So there are huge problems with the delivery of gene editing to the body. And there are huge problems with modeling. So we focus on data and modeling. And there are multiple companies focusing on different directions. So to put it, I'm sorry, yeah, we'll go faster. So there are multiple levels of organization in the body, so from atoms to the whole body. And what we have now in terms of frontier of what the large models can do for biology is modeling the biological molecules. So there are systems that can model how the proteins would fold. There are some new advancements which can give us a lot of results in biochemistry, so we can understand how the micromolecules interact with each other. And eventually, with a lot of data generation and experiments, we'll get to modeling the chemistry. And then we'll need to model the biological process. And when we understand what we want to change, we'll of course need to be able to deliver these changes, but first we need to model them. So eventually we will be able to make cell reprogramming for different types of tissues and conditions, and eventually rejuvenation, but we're not there yet. One of the biggest problems is this computational complexity and not being able to model it directly, but there are a lot of other problems. So yeah, the biggest problem is that this is just a very oversimplified picture of some of the processes in cellular biology. So a lot of things influencing a lot of things, and not very direct. We cannot infer the causality. We just get a lot of data that some things are happening, but it's not easy to understand why they're happening, so we need a lot of experiments to be able to infer this causality. And there have been a lot of attempts to model the whole cell. Like there have been different approaches, and for now we have very, very simple models in very, very simple terms of some of the processes. So it's like because of this complexity. And
love big numbers, but this.
No, we don't want this. Yeah. So a few words about how the cell works. So we probably all know that there are DNAs, which are coding the information on how the cell should act, and different cells have the same DNA mostly, but then they act differently based on what this cell type is. So the DNA is transcribed to RNA, and then RNA is translated to protein, and to put it simply, this is the basic process that is happening in biology. So the proteins are molecular machines that are doing most of the job in our bodies, and it's happening because DNAs are transcribed to RNAs and translated to proteins. Of course, it's more complicated. Not all the RNAs are coding the proteins, but some of them are just influencing the regulation of these processes, and the proteins go through modifications, and they also influence a lot of processes, and there are epigenetic changes, and there are metabolites, and most of these things, and there are also lipids, microbes, and so on, and they have different omics. So we have epigenomics, genomics, transcriptomics for RNAs, proteomics, metabolomics, and so on. So in terms of data, we have much better. I will not go directly about each of them, but to put it shortly, if we had perfect proteomics, if we understood the states and changes of the proteins in the cells, would be able to infer a lot of information because they are the most important data source. But experimentally, it's extremely hard to capture the proteins directly and with high resolution. So we just have a lot of problems in terms of experimental protocols which would allow to capture this. We have a lot of advancements now, but for now we have had much more progress with transcriptomics, and the amount of data there is orders of magnitude larger than in all other omics combined. Yeah, I will not So we can say that we've had a decade of single-cell transcriptomics, and Nature, the journal Nature Methods, publishes the Nature Method of the Year each year and discusses the most important advancements, not only in biology. And for the last 10 years, a lot of these advancements were related to single-cell transcriptomics. And the amount of data is growing faster than the Moore's law, so it's growing faster than the number of transistors on the chip. So we'll obviously have many, many more data soon, and some other graphs about growth of resolution and so on. So we want to measure these things. We want to measure how the cells are positioned and what is happening inside these cells. And we have better and better data here, and we'll have much more data soon. Then we want to model how the cell state changes when you do something to the cell. So we want to understand if we use a small molecule, how does it change gene expression, and eventually how it changes the proteins that the cell produces, and what work does the cell do. And also we want to measure it over time. So we want to understand how the different cell processes influence other cell processes, how the cells communicate with each other, how the cell does any signaling to itself, and so on. So these are estimates from my co-founder. I'm not a biologist myself, and he's been on the forefront of data generation for many years. And he expects that like the most obvious thing that we'll do next is understanding the space locations. And yeah, so the hope of AI, why do we actually expect that, given all these complexities and problems, we'll be eventually able to model this? So this is the graph with different machine learning systems eventually overcoming the humans in doing different tasks. So 0 is the baseline for humans, and for many tasks, and more to come, the machine learning models overcome the humans eventually. Why is it possible, actually? So the potential space of, for example, with texts. Why can AIs understand the texts, and why can they eventually predict the next token with this good probability to be correct? To be reasonably good for the things that they want to optimize? Because the potential space of the texts is extremely big, and there are many texts that can be generated, but most of them don't make sense, and only some small amount of the potential texts makes sense from the point of view of describing physical reality or having some concepts like human creativity and so on. So only very small subset of the potential space of the texts is reasonable, and because of that, if we understand how to reduce the dimensionality of the space, then we can make optimization tasks in this. Then we can solve the optimization tasks. In a similar way with the images, most of the images that you can generate are relatively useless, and only a small amount of the images makes sense. In a similar way with the proteins, potentially there could be 10 in degree of 300 proteins, but nature implements only 10 in degree of 10. So very small subset of the potential space is actually implemented in reality, because the proteins were the result of evolution, so there was a lot of copy-paste, and most of the solutions were never tried. And in a similar way, we believe that the cell states are also space which can be reduced in dimensions, because most of the cell states are physically impossible, most of the changes between cell states are physically impossible, so there are a lot of similarities in terms of how we can expect that eventually we will be able to learn with the machine learning models the changes in these spaces. This is a funny graph. This is expected years until general artificial intelligence comes, based on the expectations of the experts in the field. So it has been declining, and yeah, if these trends continue, we're soon hitting this. And to put it shortly, we can think of molecular biology today as NLP in mid-2010s. So we already have a lot of data. We already have some models which can do some predictions in some specific conditions with a lot of limitations, with a lot of noise, and with a lot of problems. We can make some pre-trained models that can be then fine-tuned to specific tasks. We don't have really foundation models that would be able to model the whole biology, and it's unreasonable to expect them in the next years unless we have a real artificial intelligence. But will be eventually able to predict how the cell states change based on what you do to them. And this will allow to carry out the experiments much faster. And for therapy development, there are a lot of critical places where if we have the digital experiments, we would be able to develop the therapies much faster. So for now, for example, when we want to see how the gene modification influences the cell, we have to do the experiment. And if we can have, for example, hypothesis like a few thousand genes which we want to test, we have to make a few thousand experiments. And if we want to make the test of how 2 potential gene changes would influence the state, we have to do a few thousand multiplied by a few thousand experiments, which is physically impossible already. So potentially a lot of problems like that would be solved with the models that can do this in silico. Yeah, the last point, to put it shortly, what is happening in terms of AI for drug discovery? So the first generation of the companies that went into this direction was using black box models. So we put the, okay, first of all, software 2.0, so coined by Karpathy. Previously we developed the software when we have the logic, I mean humans. Humans use the logic, humans provide the data, and the software makes the desired outcome. The concept of software 2.0 is that the humans generate the data, the humans they explain to the model what they want as a result, and then the model finds the logic which produces the wanted result from this data. We believe that software 3.0 is coming, at least for biology, when the humans only explain to the model what they need as a result, and the model uses the existing data, derives the logic, and suggests the next most important experiment. So we will eventually close the loop, and the models, so the first generation of AI for drug discovery companies was just generating some data and making some models. Then there was the next generation of the AI for drug discovery companies that were doing massive generation of data for these models. And the upcoming, like including us, hopefully, generation of AI for biology companies both generate data based on the model's predictions and build the models to derive the like how everything works. So step by step, humans are getting to make more high-level tasks, and the tasks that were previously high-level become low-level. For example, protein fold was previously the potential topic for like dissertation in PhD, and like a lot of people would work to make one protein fold eventually completed, and in terms of modeling. And now it's done on the computer, and more tasks will be done eventually on computer. So, yeah, takeaways. So we will eventually be able to model the biological processes in silico. Of course, we'll still need to always use the data from the real world and from experiments to check, to improve the protocols and so on. And the crucial issue here is data generation. There are a lot of cool initiatives for data generation. There are a lot of cool startups doing different parts of this. And we'll get there. And the timing depends on how much resources humanity spends on this. So it's a very direct influence of resources spent on data generation. And there are some initiatives which are now trying to like help researchers and different companies generate the data sets that would be available for everyone. So yeah, if you can support such projects that generate a lot of data, please do. And yeah, thanks. Is there any time for questions?
So, yes. So, Victoria taught us to embrace awkwardness, and I will do just that. What is foundational model? Can you explain in a very simple words, like I'm a 5-year-old or like 10-year-old?
There are different approaches here. The one I like is foundational model is the one that can predict things that it didn't see, and preferably things that are different from the things it saw. So mostly the models can do interpolation. So you show them this, you show them this, you show them this, you show them this. Okay, it can do something in the middle with some probability. And if the model really reaches this foundation level, like what people mentioned with language models or with image models, that we can train the models a lot on these points, and sometimes it solves the tasks that it wasn't trained to solve directly. So like the important result would be being able to somehow learn from some small subset of the data how the things out of the training set would work.
So do I understand correctly that you want to do ChatGPT for transcriptomics data?
In some way, well, we actually make the synthetic biological data to do this, because all the points are very far from each other. There is a 20,000 dimensional space, and every experiment is very far from other experiments. So it's not easy to interpolate between these experiments. So we, based on experiments, generate a lot of similar digital experiments to, like, we actually are now in the process of creating the way to produce more reasonable synthetic data.
Cool. Do you understand?
I don't understand myself, actually.
So, we have time for one or two questions. Okay.
How does it, because I don't know if that actually encompasses using code. Oh, sorry. Okay. So how would that be different, for example, the approach that you're exactly using? How is it, for example, different from the approach like Google DeepMind is using for AlphaFold, or what was used for Rosetta Fold or Chromax?
Yeah, approach is relatively similar. Take a lot of data, make the model, like make predictions, check if these predictions are reasonable, retrain the model based on the results, and so on. So the general approach is very similar. In terms of task being solved, AlphaFold is working on the level of biomolecules. So it's currently more on the chemistry level. So how the molecule would look like, how the big protein would fold, how the molecules would interact with each other. So it's more chemistry level. And what we want to tackle is the systems biology, so how the genes work to make other things in the cell change. Okay, so it's a different data modality.
Okay, so yeah, but then what would exactly be, like, how would you aim to accomplish that if the approach in general is not so different from what AlphaFold is doing? Like, how would you get from the level of AlphaFold to the level of proteomics, for example?
My expectation is that there will be multiple companies working with different kinds of cells, different conditions, different specific issues to solve. So there will not be one model that would solve everything. All the systems are very different from each other, and it's not possible to generate enough data to help computers learn all biology quickly. And different companies will focus on different applications. There will be probably hundreds of companies building reasonable models of different parts of biology. And we're not trying to be different, we're trying to solve the issues that are possible to solve now. And yeah, there are too many different issues. So what we aim to do is we want to be having the way to generate meaningful synthetic data based on the data that we have. So we have a lot of static data, and we need the data in how the cell state changes, and there are some ways to do this.
Yeah, my understanding of it is the following. The guys are one of the best in the world in enhancing RNA data, and they know how to model a lot of RNA, synthetic RNA data from it. So that would be like a first year advantage. And after that, we shall see, probably there will be much more data available, and yeah. So they will focus on that part, right?
Yeah.
Okay, one last question. Gio?
Do you think, looking at your approach with synthetic data and, let's say, automation, are there other ways we should maybe change how we generate these data, or how we change how we do science, basically, to enable these foundational models? Maybe some thoughts?
I'm not a visionary in biology. I mostly listen to visionaries and try to be very, very skeptical initially, but very optimistic about the eventual ways, and then trying to find how we can get there. I think we have huge advancements in spatial transcriptomics and also spatial proteomics and metabolomics to a lesser extent. So we have a lot of new data upcoming. We have a lot of data generated from single-cell transcriptomics and proteomics. So I think that we don't need, there are a lot of advancements already happening. There is a wave. The biggest problem is biopharma business model, which is making all the companies protect their data. So there is a lot of work being done in a very similar way in different places. So a lot of resources are spent relatively uselessly. At the same time, we don't have a better way to do this. So a biopharma business model can be blamed, but it produces a lot of results. So even given all these long times for development of things and so on, even given that FDA is so strict sometimes, basically FDA usually asks like, is it safe? Is it working? Can you prove it? I think there's a nice questions. But at the same time, we don't have enough data generated publicly. So I think that the potential biggest unlock would be when we would have much larger data sets available for everyone. And this is already happening, but the speed of course is not good enough. Yeah. Victoria?
Okay, this needs to be charged. So the data problem that we have, the data collection, do you see any solution in which we can gather data from citizen science, for example? Like they're doing so much biohacking, they're collecting so many biomarkers. Is there a way or a platform, or how do you envision, or how do you think that can be put together in a way that, okay, we have a huge database right now, and we can use that in order to create something like a model?
Yeah, I think that we have now these trackers and homemade tests and a lot of ways to get this data. It's not exactly what we would use, because in our case it's more complicated experiments and more massive data generation, and most of the data that we would use will be probably made on mice and then transferred with some loss of signal to humans. But in general, this real-world data for biopharma is a huge movement, and more and more companies are trying to come up with new protocols for clinical trials to see the patient in real time and so on. So at this point, it's much more about treating the disease and not treating how the things change in real humans. There is a huge problem with biomarkers, and I hope that there will be the talk about this soon. And we don't have good biomarkers of aging. We have multiple approaches, and they work with some noise. And yeah, I think that eventually the data from the healthy humans will be extremely important, because we measure a lot of things in pathologies. But to understand what is the pathology, we need a lot of data on the normal conditions. So this will be extremely important.
Round of applause.
Thanks.
We'll have a chance to speak to Dima afterwards. He stays here until tomorrow, so catch him and he will explain you more. And now let me introduce another Zelarian, full-time Zelarian, Leo Nissola, award-winning immunologist, author of a bestseller,